Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on halogen compounds. So this is topic 14 for the CIE specification. So this is for the Cambridge Internationals. So obviously this topic we're going to be looking at obviously compounds that contain halogens in them, so haloalkanes or halogenoalkanes, and their reactions, and looking at some radical reactions as well. So if you're studying the CIE specification, then obviously this video is perfect for you. It's exactly the right place where you need to be. There's a full range of A-level videos for all the topics for CIE on Allery Chemistry YouTube channel. Just hit the subscribe button. That'll be brilliant just to show your support. Obviously all the information on here as well, this is just made from PowerPoint slides. They are available to purchase, and I've bundled all the kind of organic year one stuff together, but you can also buy the full year one and year two specification if you're doing the full A level, of course. If you click on the link in the description box, you'll be able to purchase from there. They're great value for money and good for kind of supplement your revision. All right, okay, so let's have a look at the first topic, or the first part of it. You'll probably find there's a lot of the CIE topics kind of overlap, so you might see bits and pieces here from previous topics. There's no harm in going through it just to make sure that you understand what's expected of you. But we're going to start, probably the most sensible place to start is naming halogenoalkanes, obviously the nomenclature side of it. So halogenoalkanes, they're basically alkanes with one or more halogens attached to them. So obviously halogens are your group 7s, remember. So you've got obviously fluorine, chlorine, bromine, iodine, etc. So the first thing, like you would do in any form of nomenclature, is you need to find the longest carbon chain, and this will form obviously the last part of the name, as you're going to see in a moment. And then the names and positions of the halogens in the molecules come first. So that's classed obviously as a prefix, so it's anything that comes before that. And the prefixes in this case, because we're looking at halogenoalkanes, or also known as haloalkanes, are fluoro, chloro, bromo, iodo, and obviously we use their numbers, or the numbers on the carbon chain, to say where they are. So, and they must be in alphabetical order. That's really important, okay, because if you don't put in alphabetical order, it's not going to be right, okay? So if there's more than one halogen or different type of halogen in there, it's got to be alphabetical, not numerical, okay? I think that's a bit of some people will kind of put the numbers in order, and I know it's tempting to do that, but it must be alphabetical. That's the priority. And obviously if you have more than one type of the same halogen, so it might be di for 2, for example, it might be dichloro or dibromo, tri is 3, tetra is for 4. So let's have a look at some examples here. So here's one here. So this is, obviously you've got 3 fluorines, a carbon and a hydrogen. And so this is trifluoromethane. Obviously you've got 3, as you can see there, 3 fluorines around the carbon in the middle. So it's methane, it's got 1 carbon. This one is going to be 2 chloropropane. So obviously the chlorine is on the second carbon of a propane molecule, which has 3 carbons on it. And this one's going to be quite long. This is 1 bromo, 1,1-dichloro, 2 iodoethane. Okay, so it's always got to be in alphabetical order. That's really, really important. Okay, so obviously the ones signify which carbon it's obviously on. In this case, it could be either, to be honest, but you would try and make obviously the carbon 1 as the one with the most functional groups attached to it. So that's carbon 1, and obviously that will be 2. So try and kind of aim for that when you're naming these as well. Okay, so fairly straightforward. Again, you should have seen this in the Introduction to Organic Chemistry topic when we looked at nomenclature, or how to name compounds. Obviously, this just specifically looks at chloroalkanes, or halogenoalkanes, should I say. So, as you've seen, halogenoalkanes have the functional group X, and that's in its homologous series, so that's the family that it belongs to. And you get different types of halogenoalkanes, very similar to alcohols as well, where you get various different forms of this. So this, for example, is a primary halogenoalkane. Now, primary halogenoalkanes have a halogen that's attached to a carbon that is attached to one other carbon. Okay, so that means it's primary. So look at the halogen. Obviously, that's attached to a carbon. It's how many other carbons this is attached to. If it's attached to one other carbon, which is this, then it's a primary. So that will be chloroethane. Secondaries, you've got the halogen, which is attached to a carbon. And if that is attached to two other carbons, for example there, then it's a secondary halogenoalkane. And tertiaries, as you probably might guess, is a halogen bonded to a carbon, and that's bonded to three other carbons, and that class is a tertiary. So really what you're looking for is obviously the halogen is always going to be bonded to a carbon in this case. Then you've got to look at, well, what's that carbon bonded to? How many other carbons is it? And that will give you an idea if it's a primary, if it's a secondary, or if it's a tertiary. And obviously here's some examples here. So just make sure you're aware of them. Okay, so kind of using this, we looked at bond polarity in the bonding topic, which I think is topic 3. And so again, this is just kind of using that information from the previous topic and bringing it into obviously context of halogenoalkanes. So halogenoalkanes, they do have a polar bond, and they are attacked by nucleophiles, okay, which you will have seen as an introduction in the introduction to the organic chemistry topic. Okay, I know I keep referring back to these topics, but they really do kind of interlink. So make sure you kind of build yourself up for this and kind of look at them topics. If you're ever in doubt about what I'm saying here, go back to the topics where it's first introduced, because then you'll see it. So let's say this one, for example. So halogens are electronegative elements, so they pull electrons towards themselves in a covalent bond, okay? And obviously this leads to a permanent dipole that's being created. So you can see here you've got a delta negative chlorine and a delta positive carbon, as you can see on there. So this polar bond means that actually halogenoalkanes can be attacked by an attacking group, and in this case it'll be nucleophiles. So nucleophiles are substances which can attack substances or attack chemicals like halogenoalkanes. So a nucleophile, just a reminder, is a substance that is an electron pair donor. Okay, so it'll donate electron pairs, so it must have a lone pair of electrons. And some classic examples of nucleophiles. Remember, nucleophiles are nucleus loving, so they will go towards, well, positive nucleuses or nuclei are positive. They're not actually going for the nucleus, but a nucleus is basically has a positive charge. Nucleophiles will attack atoms which have a positive charge or delta positive charge. That's what they'll go for, because they've got a lone pair of electrons. So classic examples are ammonia, hydroxide ions, and cyanide ions, and you can see some examples down there. So curly arrows, and this is where you start to look at mechanisms. Mechanisms help us to show what's happening with a reaction. It allows us to kind of draw a picture basically of what's happening in a reaction. So curly arrows, these show the movement of electron pairs always. Okay, so all arrows always show you where electrons are moving from and where they're moving to. And in this case, a nucleophile has a lone pair of electrons. And so when we draw these, we say, right, well, this nucleophile is attacking or is moving electrons into this delta positive carbon here, because that's exactly what it's going to attack. It's not going to go for this. It's not going to go for that. It's going to go for this carbon here, okay, because that's got the delta positive charge. It's attracted to it. Okay, so let's have a look at a specific reaction using that principle. So halogenoalkanes, they react with hydroxide ions via nucleophilic substitution. Okay, so remember, nucleophile, we've seen there before. Substitution reactions are ones where you're swapping one kind of functional group or one atom for another. You're swapping it. So what we're doing is we're going to show, using a nucleophile, how we swap one atom for another, basically. That's what we're doing. So the conditions for this is it has to be warm aqueous sodium hydroxide. That gives you the source of OH- ions. It's under reflux, so you basically have the big obviously reflux column. And then you've got primary and secondary haloalkanes undergo this type of reaction. So when you obviously react them with primary or secondaries, then this will work. It won't work with tertiaries. Okay. So let's have a look. We've got a halogenoalkane here. So this is obviously chloroethane. okay, which is this molecule here, and we've got our OH minus ion there. So a nucleophile will attack the delta positive carbon, okay, so we can see it here, okay, and what it'll do is it'll replace the halogen, this, with the OH, so basically there'll be a swapping, so that's your substitution bit. So there we are. So the first thing we need to do is draw an arrow, curly arrow, from the lone pair of electrons on the OH directly to the delta positive carbon. And then what happens, this is effectively trying to form a bond with carbon. Now, carbon already has 4 bonds, and that's the maximum it can take. So one bond has to break. Okay, so this CX bond, this bit here, okay, so that breaks, and both the electrons in this bond move from the bond to the halogen, and a new bond is formed between the carbon and the OH. So effectively this is coming in, it's forming a bond with the carbon, and then this bond will break to allow that to bond with the carbon. So effectively it's like kicking it out of its house, effectively. Bit of a shame. So yeah, so it's kicking it out, and then what you have left is obviously the OH is now bonded onto the carbon, so it's muscled its way in there. This is now left on its own, but it's got the electrons from that bond, and so therefore it forms Cl- ion. And what we formed is an alcohol. So we formed a new substance. So this is a nucleophilic substitution reaction. So here's your overall reaction, as you can see on here. And you can use, obviously, R can also be known as an alkyl group. So you might see that sometimes. X is normally seen as a halogen. So you probably see these letters used to symbolize some reactions as well. Okay. So halogenoalkanes, these react with hydroxide ions, okay, via elimination as well. So what we've just seen there is a reaction using hydroxide ions as a nucleophile, but the same reaction, or using the same reagents, can actually lead to an elimination reaction instead. Now the difference here is instead in the previous one we used aqueous solution. In this one, we're going to use ethanolic solution. Okay, so that's all we're doing. We're just changing what we're dissolving the sodium hydroxide in. So we're going to dissolve this in an ethanol instead. That will give us the source of OH minus ions. It's carried out under reflux, just as before, but this time secondary and tertiary alcohols undergo this type of reaction. So primary alcohols don't. Okay, so the only thing we've changed is the condition. So make sure you're aware of that. So the hydroxide ion will attack the hydrogen on a carbon adjacent to the carbon with the halogen on. Now here, this OH is now not acting as a nucleophile anymore. So remember, nucleophiles will go for a delta positive carbon. In this case, it's not going to act as that. Because it's dissolved in ethanolic solution, it's actually going to act as a base. And if you remember, a base is a proton acceptor. So what it's going to do is it's going to react with a proton instead. Okay, so your OH minus acts as a base, it's a proton acceptor, and it's going to go and attack the hydrogen on a carbon that's adjacent to the halogen. So it's either going to be here or it's going to be here. Okay, so let's have a look. So you've got your OH minus, that's going to go in for the hydrogen atom on the top here. And then the electrons in the bond, they move to form a double bond between two carbons. So you can see here, so this is going for the proton, and then these electrons in here will move down into this bond to form a double bond, which is obviously down there. Okay. So the CX, effectively the halogen, the CX, the X represents the halogen, breaks, and both the electrons move from the bond to the halogen. So you can see here, effectively we are using the electrons, taking the hydrogen. So the hydrogen, this electrons break, they form into here. That forms a double bond effectively. Okay, so that's fine because that's got enough bonds, but this carbon will have too many bonds. So this is the weaker bond that breaks. Okay, so that's basically what's happening. So basically, hydrogen, double bond, that breaks. Okay, it kicks off that chlorine there completely. So what we form is an alkene, and you can see obviously the double bond in there. You also form water and your chloride ion as well. But this is an elimination reaction because effectively we've kicked off a hydrogen here and the chlorine here. So we haven't swapped anything, we've literally removed something. And in elimination reactions, you always will form an alkene. You've got to have that there. If you're removing atoms here, you must have that double bond completely. So the overall reaction, you can see on here, this is the overall one, and obviously we're forming KCl or the Cl-, and obviously we've got water as well. Okay, so let's have a look. We need to work out if something is going to go via elimination or substitution reactions. So the solvent, as you can see just before, plays a really important role in deciding if a reaction is going to be elimination or if it's going to be substitution. So this is kind of just summarizing this. So when we're reacting sodium hydroxide with a halogenoalkane, then we can make an alkene, as we've just seen before, when using ethanol as a solvent, or we can make an alcohol when we're using water as a solvent. Okay, so both the alkene and the alcohol with a mixture of both solvents. So actually, you can get a mixture of two if you use both solvents at once. So here you've got your halogenoalkane. This is obviously your secondary halogenoalkane because you've got the carbon. You've got two carbons either side, as you can see there. So if we react that with OH- ions and ethanol, then the OH- acts as a base. Okay, so that's definitely a base because we're obviously reacting it with ethanol. And then you form your alkene, which is here. Okay, so OH- acts as a base, removes the hydrogen, the chlorine. Look out for EZ isomerism as well, and you will have seen that in the introduction to organic chemistry topic when we look at EZ isomerism, so stereoisomerism. So just double check for that as well. Now, if we act hydroxide ion dissolved in water, so it's aqueous solution, then the OH- ion acts as a nucleophile instead. So what we form is a secondary alcohol. So the nucleophile is, obviously this is nucleophilic substitution. So we're substituting the halogen for the OH, so you form a secondary alcohol, which is here. So yeah, make sure you do check for EZ isomerism. Okay, if you're not sure on what that is, then go back and look at the introduction to AS organic chemistry, and that will have a little bit more information in there. I'm assuming you know what this is if you're looking at this topic. Okay, so let's look at some reaction mechanisms. So SN1 mechanisms, these occur in secondary and tertiary halogenoalkanes. Okay, so these reactions occur when we have an attack on the carbocation of a compound where a group breaks off completely. Okay, so we're going to look at an example here of an SN1 reaction where you've got 2-halobutane. Okay, so there could be any halogen on here, reacts with Y. As this is an SN1 reaction, the halogen breaks off and a carbocation intermediate is actually formed in this reaction here. So let's have a look. There we are. Okay, so what we've got is you've got your halogen, which is here. Now, this halogen is bonded to a carbon, which is bonded to two other carbons. So this is a secondary, as you can see, a secondary haloalkane or halogenoalkane. This is obviously going to break off first, and then you're going to have a carbocation intermediate here, and then you've got your halogen or your halide ion, which is over here. So the reaction between Y, okay, Y minus, which is this bit here. So this is your reactant, and the intermediate involves a planar molecule. Okay, so effectively, what's being produced here is a flat molecule, and we've kind of seen these as well in the bonding topic earlier. So it's got a positive charge, an actual positive charge in this carbon. Now this Y minus has a lone pair of electrons, so this is going to attack the delta positive carbon. But because it's flat, it can attack one side. So in other words, it can attack from the top, or it can attack from underneath. So you get two different approaches to this molecule, and this will give rise to two different isomers that are formed, okay, because it's planar, it can attack from above or below. Now, there's only one reactant in this rate determining step, okay, so this is where the 1 bit comes in for SN1. So obviously this is a substitution reaction, and it's just happening all in one go. So this is where we get SN1 from. Okay, so you need to be aware that when you're forming these reactions here, then you're getting this kind of, you get potentially two different isomers formed with this type of reaction. Okay, so let's look at optical activity and reaction mechanisms for SN2. Remember, they were for secondary and tertiary halogenoalkanes, so them ones previously. So we're now going to look at a reaction between a primary halogenoalkane with the same Y- ion, and this is going to go via an SN2 mechanism instead. So secondary haloalkanes, these can also proceed via SN2 mechanisms. Okay, so they can, obviously they could also kind of follow that same pathway. So secondaries, just to summarize, secondary haloalkanes can go via SN1 or SN2. Tertiary is only SN1, and your primaries is only SN2. Okay, so that's the kind of spectrum there. So with an SN2 reaction, we have a single isomer produced, unlike the two produced under SN1 mechanisms seen before. So remember, you could either approach from the top or the bottom, and so you get two different isomers. So in this case, there's two reactants in the rate determining step, and this is why we use the word 2, or the number 2 in SN2. So in an SN2 mechanism, so both the Y- and the CH3CH2X, so the haloalkane, are reacting in one step. Okay, so it's the first step, and the nucleophile always attacks the opposite side of the leaving group. Okay, so this will all become clear when I show you the diagram. So we only produce one product, and this happens mainly with primaries and sometimes with secondary halogenoalkanes as well. So let's have a look at the reaction. So you can see this is slightly different, because actually what's happening is the Y- is actually going in for the delta positive carbon here. So we're not forming an intermediate. And then the bonds in here, obviously the electrons in this bond, will move onto this halogen here. So you have this kind of dipole that exists already. And this is a primary halogenoalkane. So this is possible because there's enough space to kind of get in there and kind of get into that carbon. So what we form is this kind of a bit like if we had to kind of watch this in slow motion, a bit like a football replay, then if we had to kind of take a snapshot midway through this reaction, you end up with this. Effectively, you've got a Y trying to form a bond here, but X bond is starting to break. But you have this kind of intermediate stage here. And for a split moment, this has a negative charge, because effectively you're adding on the negative charge here. And then if we then fast forward and go to the end product, obviously you see Y is now attached on there, and then you've got X minus over here. Now all of this happens in one step. Unlike the SN1 reaction where you had an intermediate, here you don't. It all happens in one go. And this is for primaries. Primaries will go via this method. Some secondaries can as well. Okay, so this is what you're looking for. That's how you know it's SN2. Definitely primaries. Okay, for SN2, won't proceed via any other mechanism. Okay, so make sure you're aware of that, because that's going to be quite important. Okay, so let's have a look at some other reactions of halogenoalkanes. This time, instead of using hydroxide ions, we're going to react them with cyanide ions instead. So halogenoalkanes, they react with these cyanide ions to form nitriles. Okay, so the conditions we need for this are, we need warm ethanolic potassium cyanide. So obviously that gives us our source of Cn- ions. And all of this, just like all the other reactions, is carried out under reflux. So basically the nucleophile, very similar process. The nucleophile in this case is Cn-, as you can see here. There it is. And this has a lone pair, all nucleophiles do. Okay, and this will attack the delta positive carbon on the halogenoalkane, and effectively we have a substitution reaction. It's exactly the same as the OH. So again, curly arrows from the lone pair of electrons to the delta positive carbon. Obviously the halogen Cl here, so this breaks, and again the electrons move from this bond onto the chlorine. Okay, and then you form this. This is your nitrile that's been formed. Now, effectively, what you've done, you've got to be really careful with this here, is you effectively extended the length of the carbon chain here. So, whereas here you had eth, now you have prop. Okay, so you have 1, 2, 3 carbons here. So you got to be really, really careful with this, okay? So this is obviously the suffix is nitrile, but you've got propane there, so just be really, really careful with that, okay? It looks as though it's 2 carbons, but you've now added a third one, so that's 3 now, so it's prop, okay? Okay, so let's have a look at another reaction. So this is halogenoalkanes reacting with ammonia. Okay, and this is going to go via nucleophilic substitution as well. So you'll see there's quite a bit of a pattern forming here. So the conditions here, we're going to heat with ethanolic ammonia, okay, and we're going to have excess ammonia as well. We must have excess. So let's draw our molecules out again. So you can see we've got our halogenoalkane here, and this time we've got ammonia, and this has a lone pair of electrons. So this will attack the delta positive carbon, and it will replace the halogen. Okay, now the difference here is it will actually form an intermediate. This is probably a longer mechanism than the other ones, okay, but the principle's the same, okay. So you've got NH3, that's a nucleophile, lone pair going in to attack that delta positive. So let's have a look. There's your first step, no difference there. And guess what happens next? That's it, yeah, the electrons kind of break from this bond and move on to the chlorine. So you end up with this here. Now what I've done is I've expanded the NH3 bit on the end here, okay, because this is going to be quite important. There's your chloride ion that's been kicked off. So it's kind of been made homeless, which is a shame. So this is I always try and personify these, but anyway, so it's been kicked off the molecule anyway. It's been booted out, and then we have this NH3. Now the problem is ammonia now has too many bonds, so it has a positive charge on this nitrogen because you've got this bond here as well. So remember, nitrogen prefers to only bond 3 times, so it's got 4. Now this, you can probably see, this is open for attack, isn't it? Because it's sticking out like a sore thumb. So in the second phase of this reaction, we've got another molecule of NH3. Now this time, this NH3 is acting as a base. Okay, so it's a proton acceptor. So remember, this is why we have to have excess ammonia. And what this is going to do is it's going to pick off a hydrogen here. Okay, so let's have a look. There. Okay, so this lone pair of electrons is going to go in for the hydrogen here. Okay, and then the electrons in this bond are going to go into that nitrogen there, and it's going to neutralize that positive charge. Okay, so we're then going to have an amine that's formed. Okay, so this is your amine. Now, amines have got a horrible smell. They smell like fish. They've got this fishy smell. So you'll know if you've produced an amine because that's what you'll smell. Now, obviously, this ammonia is now ammonium ion. So it obviously forms this here. Now, that ammonium ion can then interact with this chloride ion that was kicked off before and form ammonium chloride. And obviously, that's your product that's produced. Okay, and that's your overall reaction. Okay, so let's look at some halogenoalkane reactivity. Obviously, we've got to understand the reactivities of these. So halogenoalkanes become more reactive as we go down the group of group 7. So what determines this reactivity? Well, as you've probably seen before in previous topics, it's the bond strength. It's the strength of that bond, and that determines the reactivity of haloalkanes. It's not the polarity of the bond. Okay, so it's not the polarity of it all. So we can see here we've got some bond strengths here. And this shows a range of different bond enthalpies of the CX bond. Now you can see the CI has the lowest bond enthalpy. Okay, so it's the lowest out of the lot of them. This means this one's going to be much easier to break than, say, a CF bond, and hence anything which is iodoalkanes, for example, iodoalkanes are much more reactive than fluoroalkanes, which are at the top, because this bond is actually weaker. Okay, so finally, let's look at some radical reactions. Now, we've seen some of these already in previous topics. This is just to kind of bring it into line with the haloalkane or halogenoalkane topic. So, chloromethane, this can be made by a reaction using free radicals. So, the overall reaction here, you've got methane reacting with chlorine with some UV light to form your haloalkane, and hydrochloric acid is made as well. So remember, you've got 3 different steps to this. You've got an initiation, a propagation, and a termination step, as you would have seen in the previous topics. So in this case, initiation is to start the reaction. Now, with the manufacture of haloalkanes, we start a reaction using UV. And basically we break the bond, so it's homolytic fission, remember, so the electrons are moving equally from one side to the other, and we form two highly reactive radicals, and you can see on there, so you've got your chlorine, break with UV, forming chlorine radicals. Propagation, so this is the propagation step is always a radical reacting with a non-radical, and it keeps the reaction going, okay? So let's have a look. So here's your first reaction. So your chlorine radical that you formed in the initiation step reacts with a methane molecule, which is obviously in the reaction. That forms HCl, and you form your methyl radical here. So that's now got the dot on there. So effectively, the radical is now passed onto the methyl. Now the methyl can then react with more chlorine. Not all the chlorine will be split, you see. You'll still have some Cl2 molecules in there. Not all of them are split with UV. So any of them which are not split, that radical will react with the Cl2. That forms your haloalkane, so this is chloromethane, and your chlorine radical. And that radical can then go back and react with more methane and on and on and on. And it will keep on reacting. You'll keep on producing this product until you get a termination stage. So termination is basically where you get two radicals colliding, and that basically they cancel each other out in some respect, and you form a non-radical substance. So for example, methane, your chlorine radical and your CH3 radical can combine to form your halogenoalkane there. So this is chloromethane. So you can see, obviously, this is definitely not a radical, as you can see. But obviously, these two reactions here, anything where you've got two radicals, you can have two Cls, for example, they will combine to form Cl2 back again. You can have these two methyl radicals colliding to form ethane. So you get a right mixed bag with this type of reaction. It's quite a very fast reaction, very useful because these radicals are highly reactive. But you do get a lot of different products that are being formed. Okay, so obviously this kind of leads us on nicely onto the products of free radical reactions. And as you just described there, chloromethane, it's really difficult to just produce chloromethane as you constantly get further reactions and you get a mixture of different products that's produced. So if there's loads of chlorine in the reaction mixture when you react to it, then what you'll get is multiple chlorination or multiple halogenation of the actual alkane. So you'll get di, tri, and tetra haloalkanes or halogenoalkanes. So you've got your chlorine radical, and this can actually react with, this is what you've just produced, which is your chloromethane. That radical can react with more chloromethane to form this radical here. And then that radical can then react with chlorine molecule to form dichloromethane, and obviously you've got your Cl dot, and then that can then go on and attack something else. And likewise, that dichloromethane can then obviously react further, following the same mechanism, to trichloromethane, as you can see there, and then that trichloromethane can react further to make tetrachloromethane. So you can see this reaction is quite uncontrollable to an extent, and if you had loads of chlorine in there, it's going to have a field day, and you're going to have loads of molecules with loads of different chlorines in there. If there's loads of chlorine in there, the likelihood of a chlorine reacting with another substance is quite high, isn't it? So we can control it to an extent, and we can say, right, what happens if we don't want all these different types of these different products, these multiple kind of halogenation compounds? Well, with free radical substitution, obviously you make all of these different substances and they have to be separated. But the way in which we can kind of control that to an extent is if we add excess alkane, so in this case it's going to be methane, then we reduce the likelihood of having multiple chlorination of this molecule, because if there's less Cl radicals in there, they're less likely to bump into other haloalkanes that have been formed to make these, obviously, these multiple substituted products. So that's a way in which you can do that. Now, it's not a guarantee. Just because you add excess methane doesn't mean you're not going to get dichloromethane, trichloromethane, or tetra. It just means you get less of them. You won't get as many of them. It's less likely to happen. So obviously, in addition to multiple substitution, we can also get isomers formed as well. And this is what I was just about to say just before until I corrected myself. And obviously, this is because obviously free radical substitution can occur anywhere on a hydrocarbon. So you might get 1 chlorobutane, you might get 2 chlorobutane, you might get, if you get multiple substitutions, might get 1,1-chlorobutane or 1,2-chlorobutane. So you might get various different reactions happening. So just be aware, always have in your mind when you're looking at organic chemistry is you might get isomers produced. And there's loads of different variations of isomer. Okay, look at the Introduction to AS Chemistry video if you're not sure on what these isomers are. You've got to be aware of all these different types of isomers. Okay, right, so that's it. That's the end of this video on halogen compounds. Hope that was useful. Like I said, the full range of A-level videos all on Allery Chemistry YouTube channel. Please subscribe and show your support. That'll be absolutely fantastic. Also, these are available to purchase via my TES website. The link is in the description box below, and hopefully, hopefully you'll find them useful. They're really good to supplement your revision. All right, but that's it now. Bye bye.